Hey everyone, and welcome. Today, we're diving deep into one of the most critical, but maybe least known parts of the internet, the transport layer. It's the silent workhorse in the background that makes pretty much everything you do online, streaming, gaming, browsing, actually work. So, have you ever really thought about this? You've got an intense game running, you're streaming a 4K movie, and you're downloading a huge file all at once over one single Wi-Fi connection. How on earth does your computer keep all that data separate and make sure it goes to the right place? It really does feel like magic, right? But it's not. It's just some seriously clever engineering, and the secret sauce is the transport layer. So let's get into it. How does the internet manage this incredible multitasking act? Well, the answer lies with its master traffic controller, which is exactly what we're going to explore first. This is the system that brings order to the absolute chaos of data hitting your device every single second. At its heart, the transport layer is basically a bridge. If you think about the internet as a stack of different technologies, this layer is sitting right in the middle. It's sandwiched between the apps you actually see and use, like your web browser or Spotify, and the low-level network stuff that physically moves data around the planet. Its main job? To manage the conversations between different apps on different computers. Now, this layer does a ton of heavy lifting for us. First, it juggles all those different data streams at the same time, which is a fancy process called multiplexing. That's how you can stream a show and browse the web simultaneously. It also takes big chunks of data, like a whole picture you're uploading, and chops it into smaller, more manageable pieces called segments. Plus, it acts like a traffic cop, controlling the speed of the data to avoid traffic jams, and it even double-checks for errors to make sure the data that arrives is the same as the data that was sent. Probably the best way to imagine multiplexing is to think of an old-school telephone switchboard. When a piece of data shows up at your computer, the transport layer looks at its port number, which is kind of like a unique phone extension for each application. For instance, port 443 is for secure web traffic, and another port might be for your Zoom call. And when you combine your computer's IP address with that port number, you get something called a socket. Think of it this way. The IP address is the street address for your apartment building, and the port number is your specific apartment number. That socket ensures every single piece of data gets to exactly the right conversation. All right, so that brings us to the two main messengers the transport layer uses to get all this work done. And first up is the super careful, incredibly meticulous, and reliable one, TCP. TCP stands for Transmission Control Protocol, and if it had a personal motto, accuracy over speed would be it for sure. TCP is all about making sure everything is perfect and in order. It's what we use for things like email, downloading files, and loading websites. You know, situations where you need every single bit of data to show up intact and in the right sequence. I mean, a web page with broken code or an email with missing sentences is basically useless, right? TCP is designed to make sure that never happens. So how does TCP pull off this amazing reliability? Well, it all starts with something called the three-way handshake. Before even one byte of your actual data is sent, the two computers have this little polite chat. Your computer sends a SYN packet, which is like saying, "Hey, you there, can we talk?" The other server replies with a SYN ACK packet, saying, "Yep, I'm here and I'm ready." And finally, your computer sends an ACK packet, which just means, "Awesome, connection established." Only after this handshake is complete does the data start flowing. And this constant back and forth is really the secret to TCP. It doesn't just throw data out into the void and hope for the best. It's always checking in. This helps it manage three really important things. First, error recovery. If a piece of data gets lost, the receiver never sends back the "I got it" message, so the sender just sends it again. Simple. Second, flow control. The receiver can literally tell the sender, "Whoa, you're sending too fast, slow down a bit." And third, congestion control. If TCP senses the whole network is getting clogged up, it will slow itself down to be a good citizen and help prevent a total internet gridlock. It's this combo that makes TCP so incredibly trustworthy.
But what if all that perfection is actually slowing you down too much? What if what you really need is just pure raw speed and you're okay with a few bumps in the road? Well, that's where our second messenger comes in. Meet UDP.
Yep, this is UDP, the User Datagram Protocol, and its philosophy is the complete opposite of TCP's. UDP is all about speed, speed, speed. It's the internet's express delivery service. It gets rid of all the extra baggage. No handshakes, no acknowledgements, no error checking. It's built for those times when a tiny bit of data loss is totally worth it to get real-time, lightning-fast performance.
So here's the absolute biggest difference between them. TCP is what we call connection-oriented. It does that whole polite three-way handshake thing to set up a stable channel before it sends anything. UDP, on the other hand, is connection-less. There's no handshake, no how are you, no nothing. It just wraps the data up in a simple packet, called a datagram, and launches it at the destination. It's the difference between sending a certified letter that needs a signature versus just dropping a postcard in the mail.
So, where does this fire and forget style actually make sense? Well, think about anything happening in real time. In an online game, waiting for a lost piece of data from 3 seconds ago is useless. The game has already moved on. You need to know what's happening right now. Same thing for a live stream or a Zoom call. You won't even notice a few dropped pixels or a tiny audio blip, but a long pause while TCP tries to resend a lost packet, that would freeze the whole thing and ruin the experience. Sometimes speed is just way more important than perfection. Okay, so now that we've met our two messengers, the reliable one and the speedy one, let's put it all together. How do developers actually decide which one is the right tool for the job? This table really breaks it down nicely. If you need guaranteed, rock-solid reliability, you go with TCP, the certified courier. It's going to be a bit slower because of all the handshakes and acknowledgments, but you know for a fact your package will get there in one piece. But if you just need pure speed and you can handle a little bit of potential loss, you go with UDP, the postcard. It's way faster and lighter because it skips all those formal steps. So let's connect this to the apps you use every single day. Sending an email in Gmail or loading a web page, that's all TCP, because you can't have missing sentences or half-loaded images. Downloading a big file, 100% TCP. But hopping into a game of Fortnite, making a video call on Zoom, or streaming a movie on Netflix, that's all UDP, where being fast is what matters most. In fact, a lot of modern apps actually use both. Netflix might use TCP to load the menu and your account info, but then it switches over to UDP for the actual video stream itself. It's all about picking the right tool for the right task. And all of this leaves us with a really fascinating question to think about for the future. In a world that's demanding more and more real-time, instant interaction, from cloud gaming and the metaverse to AI, we keep choosing the speed of UDP over the perfection of TCP. So you have to wonder, as we move forward, will that guaranteed reliability become a luxury we just can't afford? Something to think about. Thanks so much for watching.